Oh, I did not check. We'll figure it out in a little while. Okay, so this is topic 312. These are equivalent representations of trigonometric functions. Equivalent representations. So another name for this equivalent representations business is the word identity. Identity. Okay, we call them trig identities, plural. Trig identities. These are true statements regarding trig functions. Okay, so for example, you already have some identities under your belts. You already know that 1 over sine theta is cosecant theta. You already know that 1 over cosine theta is secant theta. You already know that tangent theta, well, let me change that. Let's do 1 over tangent. 1 over tangent theta, or cosine over sine, is cotangent. These are 3 identities. They're in the set called reciprocal identities. Not inverse. True that, not inverse. These are reciprocal identities. So you already know 3 identities. You also know the identity that says tangent is sine over cosine. That's an identity. So an identity is a true statement, a rule that you can use every time. Okay? Today we're going to walk through several new identities. In calculus, we use a couple of them. In pre-cal, we're going to use a lot of them. Okay, so this is going to be important for you to memorize this year and hold on to some of it for next year. Okay, but it's not going to make or break you if you forget some of them. We'll recover what we need moving forward. Okay, so the first identity or set of identities we're going to talk about is Pythagorean identities. Pythagorean identities, and these come from Pythagorean theorem. Using a unit circle and using our x and y and r relationships here. So what we see is if I can replace x with cosine theta, and I can replace y with sine theta, and I plug it into my Pythagorean theorem, I come up with this idea that sine squared theta plus cosine squared theta is 1. In other words, x squared plus y squared would be r squared. And r, in this case, is 1. So we have this identity. Sine squared theta plus cosine squared theta equals 1. Everybody cool with that? We've got 2 other ones that stem from these. Okay? So example 1 says, show that cotangent theta, or cotangent squared theta, is equal to cosecant squared theta minus 1. So I want to focus in right here on this cosecant squared. What is cosecant? 1 over sine, right? 1 over sine. So here's what we're going to do to prove that. We're going to take our sine squared theta plus cosine squared theta equals 1. And we're going to make our 1 be cosecant squared. In order to do that, we know that that's equal to 1 over sine squared theta. Are you following this? I'm focusing in on cosecant squared theta, and I know that cosecant squared is actually equal to 1 over sine squared. Are you seeing what I'm saying here? This is yes, this is So in my Pythagorean identity, sine squared theta plus cosine squared theta equals 1. I'm going to divide the 1 by sine squared theta so that I can come up with this cosecant squared theta piece. If I divide 1 by sine squared theta, I should do that to everything. So we're going to divide sine squared theta by sine squared theta. And we're going to divide cosine squared theta by sine squared theta. She says. So what is sine squared theta over sine squared theta? 1. What's cosine squared theta over sine squared theta? Cotangent squared theta. And what was 1 over sine squared theta? Cosecant squared theta. Isn't that beautiful? And they said show that cotangent squared theta is equal to cosecant squared theta minus 1. So how do I prove that? Subtract the 1. Bring that dude over here. And now I know that cotangent squared theta is equal to cosecant squared theta minus 1. Are we following? Okay. There's one more identity. Let's get it written out up here. This goes with the same. You can write yours over here. Let's just carry out this idea over here on the far left, because I think y'all have room on your papers. Am I right? Okay, so let's start out with our sine squared theta plus cosine squared theta equals 1. And instead of dividing everything by sine squared theta, let's try dividing everything by cosine squared theta. So what's cosine squared theta over sine squared theta? Sine over cosine. Tangent squared theta plus 1 equal to secant squared theta. So there's your third Pythagorean identity. Sometimes you'll see it as tangent squared theta is equal to secant squared theta minus 1. It's the same thing. Any questions? Okay, so you've got 3 Pythagorean identities. You've got the bottom one that we just proved here. And you've got this one over here, cotangent squared theta equals cosecant squared theta minus 1. Or 1 plus cotangent squared equals cosecant squared. Those work anyway, okay? And really, I would not ever have you try to memorize all 3 of them, because given the first one, you can come up with the other 2 really quickly. Either divide everything by sine or divide everything by cosine. Are we clear on that? Okay, so if you're going to hang on to one of those, that's going to be your sine squared theta plus cosine squared theta equals 1. And that just comes from straight up Pythagorean theorem. Okay, so let's go into example 2. It says use a Pythagorean identity to express 1 plus cotangent squared theta times sine squared theta in terms of cosecant x. So do you see this 1 plus cotangent squared x? You see this piece of information? Well, the identity that we have says that that piece of information, 1 plus cotangent squared theta, is what? Cosecant squared theta. So what if I substitute that in? Cosecant squared theta, or cosecant squared x, instead of 1 plus cotangent squared x, because now we can see those are equal, times sine x. And what is cosecant? 1 over sine? So this is actually going to be 1 over sine squared x times sine x. You can cancel one of the signs with this top sign, and I have only 1 over sine x, which is now cosecant x. So we use this identity to substitute in and then simplify. And now we can say 1 plus cotangent squared x times sine x is cosecant x. We can tell those are the exact same thing. Identities are some of my the coolest things. This is my first time ever to get to teach them, but I think they're pretty neat. I took pre-cal in high school, and my mom taught it to me, and she was all about identities. I mean, she made us walk and talk with identities. So I was good at it, but I haven't ever taught it before. It's kind of interesting. All right, example 3. Example 3, it says, use a Pythagorean identity to express 3 cosine cubed x over 1 minus sine squared x in terms of cosine. So that kind of gives you a hint as to what we're trying to substitute out. Do you see this 1 minus sine squared x business? This down here on the bottom? 1 minus sine squared x. Can you tell that if we rewrite our cosine squared x plus sine squared x equals 1, if we rewrite that and subtract that sine squared x off of both sides, that is cosine x, cosine squared x? Can you tell that? This is yes. This is So instead of having 1 minus sine squared x on the bottom, what could we call it? We can call that cosine squared x. And we're using an identity to substitute. Well, now I have 3 cosine cubed x over cosine squared x. That's a cosine, cosine, cosine on top and a cosine, cosine on bottom. So what cancels? Right. How many are we going to have left? I'm going to keep 1 on top. And my answer here is going to be 3 cosine x. If you're sleepy, go stand up. You're bobbing for apples. You and Austin are having an apple dipping contest. You want to stand up? You do not want to stand up. Would you rather just take a nap and leave you alone? Don't take a nap. You'll miss this. You'll be so sad. Yeah. Look down for 1 second and we were gone. Okay, so on the bottom we had 1 minus sine squared x. Do you see that? If I use my Pythagorean identity and rearrange it, I can see that cosine squared x is equal to 1 minus sine squared x. Can you see that? So on the bottom, I swapped that out and I put cosine squared on the bottom. So now I have cosine cubed on top and cosine squared on the bottom. If I divide those, all that's left is 1 cosine squared on top with the 3. So I have 3 cosine x. How are they equal?
What makes them equal?
You take the Pythagorean identity that says cosine squared plus sine squared is 1. Swing the sine squared, and cosine squared x is equal to 1 minus sine squared x. I tell you, you're going to be so sad. Don't go. Don't leave me.
I understand cosine squared plus sine squared equals 1.
Yes. Subtract
But-
sine squared x on both sides.
When you subtract sine squared x on both sides, there's only 1 on this side.
Right.
So you have sine squared x minus 1.
No,
And
1
then-
minus sine squared x. Okay.
And then you would have cosine squared on this side.
Right.
You have
So
3
on the
cosine
bottom,
cubed.
look at the bottom.
Yes.
It's only 1 minus sine squared x.
Yes.
That's the one we're replacing.
Does cosine squared x in?
So that you would swing it over that side. So they would be equal. You're so smart. Goodness gracious.
Okay. Now he's awake. Now he's awake.
No way can we start that.
Lies. Okay, here we go. On the next page, these are your sum and difference identities. Sum and difference identities. And this looks like a whole lot of ooh. Here's how this works. Okay, this is how you can remember these. You ready for this? It's scary. These look scary, but they're not. Okay, so both sine ones are going to lead with sine. Can you see that? On the sine sum and difference identities, both of them go sine, cosine, sine, then cosine. On cosine, they both start with cosine and they both have cosine, cosine. Cosine, cosine. Your sine ones alternate. So there's a bottom, so yours are split into two boxes. For some reason, when I took a picture of it, it was nicer. It's split into two boxes. Okay? So the sine one involves both sine and cosine on both terms. Both have both pieces. The cosine ones only have cosine on the front terms and only have sine on the back terms. Can you see it? So sine alternates. Sine, cosine plus cosine, sine. Sine, cosine minus cosine, sine. Cosine goes cosine, cosine, sine, sine. Cosine, cosine, sine, sine. Can you see it? Cosine is also a liar. And I think Jenna just picked that up. Cosine's a liar. Check it. On cosine, you have alpha plus beta, which are the names of the angles. In your identity, if it's plus for cosine, it's subtracting the two terms. He says if it's inside with the x, it's going to lie. Cosine is an x.
Yeah.
So cosine's a liar. Okay? So cosine's lying. And your sines alternate. Sine, cosine, cosine, sine. Sine, cosine, cosine, sine. Cosine has cosine, cosine, sine, sine. And it's a liar. Okay? Are we following? Like, can you understand these rules? Because it looks daunting, but they're really not that bad if you can see how to use them. Okay, so let's attack this example 1. And it says, use the fact that pi over 3 plus 3 pi over 4 is 13 pi over 12. So what they're saying is find cosine of 13 pi over 12. And they gave you a huge hint. They said use the fact that 13 pi over 12 is equal to these two fractions. So we can call cosine of 13 pi over 12 cosine of pi over 3 plus 3 pi over 4. We can split that argument into two arguments that are being added, which tells me which function do I want to use, which of the sum and difference identities. 1, 2, 3, or 4? 3. Because we have two separate angles that are being added, and we're doing cosine of those angles. Can you see it? So we're going to write this out using this format. And we know that cosine has cosine, cosine, sine, sine. And we know that cosine's a liar. So this is going to go cosine pi over 3 times cosine 3 pi over 4. It's a liar. Minus sine pi over 3 sine 3 pi over 4. Yeah? And then we evaluate. What is cosine of pi over 3? 1/2. Good. That's a half. Cosine of 3 pi over 4?
Square root 3. No.
It's negative.
Negative square root 2.
Okay. Minus, open parentheses, sine of pi over 3. Square root 3 over 2, that's a tall. Square root 3 over 2, that's what that says right there. Sorry. Sine of 3 pi over 4. Okay. Y'all following?
Yeah.
Then you pull out a calculator. No, it's okay. We'll just simplify. We want exact values here. So in the first term, that's going to be a negative square root 2 over 4. Multiply across the top, multiply across the bottom. Minus Square root 3 times square root 2 is square root 6 over 4. And this is about as good as we're going to get it. They call it negative square root 2 minus square root 6 all over 4. Since we're all over 4, you could combine the numerators. Okay. What do you think? Not too bad? Okay. Use a sum or difference identity to evaluate. Look what we have. We have cosine, cosine, sine, sine. So this is automatically a cosine one. And if it's a cosine one, it's a liar. So we're going to use cosine alpha plus beta, except it's going to be cosine alpha minus beta. Why? Because it's a liar, because it's a cosine. Cosines are liars, and they go cosine, cosine, sine, sine. Are you with me? Everybody good with this? Okay, so if my two angles are alpha and beta, then I'm going to have cosine of, what's alpha?
5 over 18.
Minus beta.
5 over 9.
Woo woo. And we can common denominator here. So times 2 over 2. Right?
Yeah.
So we've got cosine 5 pi over 18 minus 2 pi over 18 is going to be cosine of, what's 5 minus 2? 3 pi over 18. Reduce it. Cosine of pi over 6 is, boom. Hold on. Process. Get your spinning wheel going. Buffering. Common denominator is 18. Once you have that, combine your numerators and then simplify. So cosine of pi over 6. So it's actually not so scary once we kind of have an idea of what we're doing here. What do you think? We do okay with that one? Oh, double angle. Double angle actually we do see in calculus. So these two will probably come back up.
This lesson is done.
No. Okay, so show that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. This one was a little bit more out there for me. Cosine 2 theta. Let me get you going here. We're going to call that, instead of cosine 2 theta, we're going to call it cosine of theta plus theta.
Which is equal to cosine squared theta minus sine squared theta.
Okay, we're just going to work with the one side. When we do identities, it's really helpful to just focus on one side of the equation and then get to the other side. We don't want to go adjusting the other side. We want to work on the left side and make it look like the right side. So cosine of theta plus theta. Now we can go back up into our sum and difference identities. This is a cosine. So it's going to go cosine, cosine. So cosine theta times cosine theta. And it's a liar. So minus sine theta, sine theta. Well, what's another name for cosine theta, cosine theta?
Cosine squared theta.
Look at y'all. Cosine squared theta. Minus.
Sine squared theta.
See, we did it. We showed that cosine of 2 theta is cosine squared theta minus sine squared theta. These are proofs, like geometry. Oh, but if it didn't say that, we would have been okay with it, right? Okay. But you were liking this. These are trig identities. These are not proofs. These are not proofs. These are showing that, not proving, showing that the identities work. Okay. All right, here's example 3. Write the following expression in terms of a single trigonometric function. So we've got sine of 10x. Here's your clue. On the bottom, they have cosine of 5x. So instead, what if we write that sine of 10x as sine of 2 times 5x? And the only way you know to do that is because you can see your angle in the bottom is 5x. So now if we go back up here to our double angle proofs, or identities, double angle identities, you see that sine of 2 theta is equal to 2 sine theta cosine theta. Are you seeing it? So instead of sine of 2 times 5x, we can call that 2 sine of 5x times cosine of 5x. Well, we're using this angle up here, 2 sine theta cosine theta, and theta is 5x. So we have 2 sine 5x cosine 5x divided by 2 cosine 5x. I didn't mess with the bottom at all. Now what cancels? 2's and cosine of 5x. So a single trig identity here is going to be sine of 5x. It says write the following expression in terms of a single trig identity. And we did. One single identity, sine of 5x.
That's cool. No, because I thought you moved your 2 cosine 5x up to the top.
No.
Your sine into an angle.
Right. So we replaced sine of 2 at 5x with its identity function.
Yeah.
How we doing, y'all? Pretty good?
Good.
Okay. All right, one last page. Oh. It is is that a sign chart I see? Yes. Okay, so example 1, we can use these identities. So once you kind of get familiar with what the identities do for you, they shortcut it. They help. They are super helpful. They take something very long and seemingly daunting, and turn it into something manageable. They are shortcuts. Okay? So it says use a trigonometric identity to solve for x. So right here we have sine of 2x, and that should trigger a thought. 2 sine theta cosine theta. So let's replace that sine of 2x with 2 sine x cosine x plus 2 cosine x equal to 0. Anybody have a next thought? Y'all are wanting to subtract the 2 cosine thetas?
Yeah.
Or wait, what if you
Divide by
factor x?
He said, I like that option the best. He said factor cosine x out. Because both terms have a cosine of x. Do you see it?
Yeah.
Both terms have a 2 cosine x. So let's factor that guy out. 2 cosine x, and what's left? Sine x plus 1. Be careful. If you pull that 2 cosine x, you're leaving a 1. Equal to 0. Now what? We've got a product. We've got a product of 2 things. The zero product property says if the product equals 0, 1 or both are 0. So set them equal to 0 and solve for x. So 2 cosine x equals 0.
Yep.
Divide by 2, divide by 2. We're left with cosine x equals 0, or x is cosine inverse of 0, which is cosine x equals 0. I divided by 2. It canceled on both sides. So x is cosine inverse of 0, which asks the question, what is the angle where cosine is 0? pi over 2 or 3 pi over 2. So x is equal to pi over 2 and 3 pi over 2. That's one of our factors. These are our answers.
Now sine of x
Our-
would be negative.
Okay, so now sine of x equals negative 1. Very good.
So that would be
X equals
sine
sine inverse of negative 1. I'm hearing it back there. X equals, where is sine negative 1? 3 pi over 2. And we already got that answer as one of our options. So could be. No, it's not a whole. They're both continuous. Okay?
An oscillation couple.
Okay? No, not if you're dealing with continuous functions. There's no reason to have a whole. Okay, now it says use your work in example 1 to solve for when this is greater than 0. So we already know our zeros happen at pi over 2 and 3 pi over 2. So now we want to plug a number into our function, our factored function. I think we want to plug in right here and see whether we're positive or negative. So I plugged in pi over 4. 2 times cosine of pi over 4, that's going to stay positive. Sine of pi over 4 is positive. Plus 1 stays positive, so I'm positive on that interval. I went like a dummy head and split this into 2 intervals, and that's stupid. You should just plug in pi, right? So cosine of pi is negative 1. Sine of pi is 0 plus 1, so we're negative there. And then I plugged in 7 pi over 4 on this interval. Cosine of 7 pi over 4 is positive, but
if you
add 1 to it, and it's enough to get it out of the hole. So we are positive greater than 0 on the interval from 0 to pi over 2 and 3 pi over 2 to 2 pi. How are we on the sign chart business? I thought I had to split the middle one. I don't know why. Pi is not a 0, but I split it. I'm telling y'all, like, whoa, brain fart. Okay, last one. It's going to take us about 5 minutes, so y'all hang in there. Okay, we got this. Use a trigonometric identity. Can you tell that in the argument they're adding 2 angles? So this is a sum or difference identity. Hint, hint, it's a sum because they're adding, right? The sine ones alternate. Sine, cosine, cosine, sine. The cosine ones are the ones that stay. Cosine, cosine, sine, sine. Okay? So these ones alternate. So sine of x plus pi over 6 is going to equal sine x cosine pi over 6. Sines tell the truth. So plus cosine x sine of pi over 6. They alternate. Y'all doing okay here? Everybody all right? Now, we cannot evaluate sine of x because we don't know what x is. We can, however, evaluate cosine of pi over 6. What do we know that number to be? It's a long. So we can call this square root 3 over 2 sine x. Right? We're saying that this cosine pi over 6 is square root 3 over 2. And then in the second half, we've got a sine of pi over 6. What can we call that? Half. So plus 1/2 cosine x equal to 0. What am I hearing? Multiply times 2. I love it. I love a good option. Times 2. Everything. Everything. Multiply by 2. What happens on the right side with the 0 times 2? 0. Say nothing. But I've got square root 3 sine x plus cosine x equal to 0. Anybody got another option? Can't separate x from the arguments, from the trig functions. Subtract cosine x. I like it. Subtract cosine x, question mark? Yes. Okay, so now I'm going to move over here where I've got some blank space. I have square root 3 sine x equal to negative cosine x. I'm going to tell you one thing that my little brain had in mind. The square root 3 makes me think tangent. Because I don't have a square root 3 over 2 anymore. My 2's are gone. And so now I have a square root 3, and I know tangent involves either 1 over square root 3, or I sometimes get square root 3 over 1. So I started gearing up trying to find a tangent in here somewhere. Divide by cosine, because tangent's sine over cosine. So if we'll divide both sides by cosine x.
You have negative square root 3. You should put your
No, I didn't divide by negative 1. I just divided by cosine. So I have square root 3. Now what's sine over cosine? Tangent x equal to negative 1. Ah, now we're cooking. Then what? What you got next? You were? Divide by your square root 3. So tangent of x is equal to negative 1 over square root 3. That means x is tangent inverse of negative 1 over square root 3. Your square root 3 is in the bottom, which means your cosine's along, and it's negative.
Which is 5 pi over 6. That's wrong.
No, that's right.
That's right.
5 pi over 6. It also happens again at 11 pi over 6. Good job. Cosine's along, and this argument is negative. So we're either in quadrant 2 or 4. 2 times cosine's long in quadrants 2 or 4. 5 pi over 6 and 11 pi over 6. Those are your two answers here. Hey, y'all did a great job today. This is hard, really hard, and I'm super proud of you. Try to do your homework. Guys, we have to move on Monday. So we won't have in-class time for your homework, but I have done it if you'd like to come in and check your solutions at any time. Okay? Okay.